When light hits an object in space, three things can happen. The light can be absorbed, converted to heat. It can be transmitted through the material, if it's transparent. Or it can be reflected, bouncing back toward the source. The fraction of light reflected is called albedo. It's measured on a scale from 0 to 1, or 0 to 100%. Perfect absorption, like a black hole's event horizon, gives you 0. Perfect reflection, a theoretical impossibility, gives you 1. Everything else falls in between. Charcoal has an albedo of 0.04. Fresh snow has an albedo of 0.9. The brightest natural surfaces we know, certain types of clouds or salt flats, reach maybe 0.95 under ideal conditions. 3I Atlas has an albedo of 0.94. That's 94% of incoming light reflected back into space, and it maintains that albedo across multiple wavelengths, from ultraviolet through visible to near-infrared. No natural material does this. Not ice, not rock, not metal, not any combination we've ever observed in any solar system object. I'm Avi Loeb, and I've spent 4 decades studying how light interacts with matter. What 3I Atlas is doing with light violates every principle of natural surface composition, and I'm about to show you why that matters. Before I walk through the albedo measurements that prove this impossibility, before I explain why achieving 94% reflectivity requires engineered surfaces, before I reveal what this tells us about Atlas's thermal management and stealth capabilities, I need you to understand something fundamental. Albedo is not arbitrary. It's determined by material properties at microscopic and nanoscopic scales. Surface roughness, chemical composition, crystal structure, all dictate how photons interact with matter. Natural surfaces are messy. They have imperfections, variations, contamination. These imperfections absorb light. They scatter it in random directions. They prevent perfect reflection. When you see an object with near-perfect albedo maintained consistently across its entire surface, you're seeing quality control. You're seeing manufacturing. In the comments below, tell me this. What natural process produces a 5-kilometer surface with uniform 94% reflectivity? Because I can't think of one. And if you can, I genuinely want to hear it. Because the alternative is accepting that 3I Atlas has an engineered surface. And engineered surfaces imply engineers. Let me start with how we measure albedo, because the method determines confidence in the result. Albedo measurement requires knowing 2 things: how much light hits the object and how much light comes back. For objects in the solar system, the incoming light is sunlight. We know the sun's luminosity and the distance to the object. That gives us the incident flux, the amount of solar energy per square meter hitting the surface. Measuring the reflected light is more complex. We observe the object with telescopes, measure its brightness in various wavelengths, and account for the viewing geometry. The object's brightness depends on its size, its distance from us, its distance from the sun, and its albedo. If we know size and distances, we can solve for albedo. With 3I Atlas, we have brightness measurements from multiple observatories across multiple observation campaigns. Ground-based optical telescopes in Chile, Hawaii, Spain. Space-based platforms like Hubble. Each observation records the object's brightness in different filters, different wavelengths. The brightness is remarkably high, much higher than expected for a comet or asteroid. To explain the observed brightness with the measured size, about 5 kilometers diameter, the albedo must be extremely high. The calculations consistently give values around 0.94 with uncertainty of maybe 0.02. That's 94%, plus or minus 2%. This isn't a one-time measurement. This is repeated observations over months showing stable, high reflectivity. Let me put 0.94 albedo in context. Comet nuclei typically have albedos between 0.03 and 0.06. They're darker than charcoal. The dark color comes from organic compounds, carbon-rich materials that formed in the outer solar system and have been radiation processed over billions of years. Asteroids range from 0.05 for the darkest carbonaceous types to maybe 0.3 for brighter stony types. Metallic asteroids, made primarily of iron and nickel, can reach 0.5 or 0.6 if the metal is clean and polished. But space is dirty. Micrometeoroids constantly sandblast surfaces. Solar wind implants atoms. Cosmic rays break chemical bonds. Natural space surfaces get weathered, roughened, contaminated. This weathering reduces albedo over time. Old surfaces are dark surfaces. 3. I-Atlas has been traveling through interstellar space for millions of years. It should be dark. Its surface should be covered in radiation-processed organics, interstellar dust, micrometeoroid impact craters. All of these would reduce albedo dramatically. Instead, it's brighter than fresh Antarctic snow. The only natural objects we know with albedos approaching 0.94 are icy moons of the outer planets. Enceladus, Saturn's moon, has an albedo of 0.99, the highest in the solar system. But Enceladus achieves this through constant resurfacing. It has active geysers ejecting freshwater ice that covers the surface in a pristine layer. Within Saturn's magnetosphere, Enceladus is protected from some of the radiation and bombardment that darkens surfaces. And even with all these advantages, Enceladus's high albedo is localized. Some regions are less bright. 3. I-Atlas shows uniform high albedo across its observable surface. As it rotates and we see different hemispheres, the brightness remains constant. This uniformity is as striking as the absolute value. It suggests the surface material or structure is consistent everywhere. No darker patches, no regional variations, no weathering gradients. For a natural object, this is impossible. Impacts, thermal cycling, radiation exposure all create heterogeneity. Some areas get hit more, some areas sublimate more, some areas accumulate more dust. Natural surfaces are patchy. Atlas is uniform. Now let me explain why 94% reflectivity requires specific material properties. When light hits a surface, the interaction depends on the surface's refractive index and roughness. Smooth surfaces with high refractive index contrast, like metal-air or ice-air interfaces, can reflect strongly. But even ideal smooth surfaces have limits. Fresnel equations describe reflection from smooth interfaces. For normal incidents, light hitting straight on, the reflectance depends on the refractive indices of the two media. For ice with refractive index 1.31 inches air with refractive index 1, the reflectance is about 2%. Most light enters the ice. To achieve high reflectance, you need high refractive index materials. Metals work. Silver has reflectance around 95% in visible wavelengths. Aluminum is about 90%. But these are pure, polished metals in laboratory conditions. In space, metal surfaces oxidize, corrode, get coated with contaminants. The reflectance drops. To maintain high reflectance, you need either continuous renewal of the surface, which requires active processes, or you need coatings that protect the underlying reflective layer while being transparent. Multilayer dielectric coatings can achieve this. They're used in high-quality mirrors and optical instruments. Alternating layers of materials with different refractive indices create constructive interference for reflected light and destructive interference for transmitted light. With enough layers, you can push reflectance above 99%. But these are engineered structures, nanometer-scale precision in layer thickness, controlled composition, defect-free interfaces. Nature doesn't build these. Another way to achieve high albedo is through structural coloration, the mechanism behind some butterfly wings and bird feathers. Microscopic structures diffract and scatter light in ways that produce bright colors and high reflectance. But this typically works only for specific wavelengths. You get high reflectance in blue, for example, but not in red. 3I Atlas shows high albedo across a broad spectrum, UV, visible, near-infrared, all reflected at similar efficiency. This broadband high reflectance is diagnostic of either metallic surfaces or sophisticated multi-layer coatings designed to work across wavelengths. Let me discuss what high albedo means for thermal balance. Objects in space reach equilibrium temperature based on how much sunlight they absorb versus how much heat they radiate. Absorbed sunlight heats the object. Radiated infrared cools it. The equilibrium temperature depends on albedo and infrared emissivity. For a body at Earth's distance from the Sun, with albedo 0.94, absorbing only 6% of sunlight, the equilibrium temperature is extremely low, around 150 Kelvin. That's minus 123 Celsius. For comparison, a dark object with albedo 0.05 at the same distance reaches about 280 Kelvin. The high albedo keeps Atlas cold. Is this intentional? If Atlas contains electronics or living systems, keeping cold is beneficial. Electronics operate more efficiently at low temperatures. Radiation damage decreases. If Atlas has cryogenic systems, superconductors, or quantum computers operating at 150 K might be necessary. The high albedo could be thermal management. But maintaining 94% albedo requires that the surface stay clean and intact. Any degradation, any dust accumulation, any impact damage would create dark spots that absorb more light and heat locally. The fact that albedo remains high and uniform suggests either the surface is incredibly durable, resisting all weathering, or there's active maintenance cleaning or repairing damage. Both scenarios imply engineering. High albedo also affects visibility. A bright object is easier to detect optically. You'd think if Atlas wanted to remain hidden, it would have low albedo, absorbing light to avoid detection. But there's a trade-off. Low albedo means high temperature. High temperature means strong infrared emission. Infrared telescopes could detect a hot object even if it's optically dark. By maintaining high albedo and staying cold, Atlas minimizes infrared signature. It's bright in optical wavelengths, but nearly invisible in infrared. This is stealth design. Not trying to avoid detection entirely, but controlling which wavelengths it's visible in. Optical detection requires looking in the right place. Infrared detection works even if you don't know where to look, because hot objects glow. By staying cold, Atlas makes itself harder to find via thermal detection. Let me walk through the spectral reflectance data, because the wavelength dependence is informative. Most materials have albedo that varies with wavelength. Ice is more reflective in visible light than in near-infrared. Organic compounds absorb strongly in UV. Metals have characteristic absorption features. Atlas's reflectance spectrum is remarkably flat. From about 300 nanometers in the UV through 2,500 nanometers in the near-infrared, the albedo stays around 0.94. This flat spectrum is unusual. It's consistent with broadband dielectric coatings, or with a surface structure optimized for wavelength-independent reflection. Think of it like an engineered mirror designed to reflect all colors equally. We make these for telescopes and cameras. Nature doesn't make them for asteroids. Now I want to address measurement uncertainties, because skeptics will argue the albedo might not really be 0.94. Fair point. Let's examine the errors. Albedo calculation requires knowing the object's size. If the size estimate is wrong, the albedo estimate is wrong. We've measured Atlas's size through optical observations at roughly 5 kilometers diameter. If it's actually smaller, say 4 kilometers, the albedo would be lower to explain the same brightness. How much lower? For 4 kilometers diameter instead of 5 kilometers, the area is smaller by a factor of 4. 5 squared equals 0.64. To maintain the same brightness, albedo would need to be 0.94 divided by 0.64 equals 1.47. But albedo can't exceed 1. That's physically impossible. So if Atlas is smaller than 5 kilometers, it's even more impossible. The only way to reduce the calculated albedo is to make Atlas larger. If it's 6 kilometers instead of 5 kilometers, albedo would be 0.9. 4 times 5/6 squared equals 0.65. Still extremely high. Still brighter than any natural asteroid or comet. The uncertainty in size doesn't save the natural explanation. Distance measurements could also introduce error. If Atlas is farther than we think, it's intrinsically brighter, which means higher albedo. If it's closer, lower albedo. But distance is well constrained by orbital mechanics and parallax measurements. We know where it is within a few thousand kilometers. That's negligible uncertainty at the scales involved. Brightness measurements have uncertainty too. Telescopes can miscalibrate. Atmospheric extinction can be misjudged. But we have observations from multiple independent telescopes, space-based and ground-based, all converging on high brightness. For them all to be wrong in the same way by the same amount is implausible. The albedo is genuinely high. Let me discuss possible natural explanations and why they fail. First, fresh ice. Could Atlas be covered in pristine water ice? Fresh ice can have albedo up to 0.9. Close, but not quite 0.94. And fresh ice doesn't stay fresh. Space weathering darkens ice on timescales of thousands to millions of years. Atlas has been in space for millions of years based on trajectory analysis. Its ice would be ancient and dark, not fresh and bright. Second, frost. Frost, fine ice crystals with high surface area, can be very bright. But frost is mechanically weak. It doesn't survive impacts. It sublimates easily. A frost-covered object would show changing albedo as the frost redistributes or sublimates. Atlas's albedo is stable. Third, salt. Some salt minerals are very bright. Sodium chloride, magnesium sulfate, bright white in their pure forms. But salts are rare in space. They form in aqueous environments, liquid water with dissolved ions. We don't expect large salt deposits on interstellar objects, and even if present, salts are water-soluble. Any sublimation of water ice would dissolve and redistribute the salt, creating uneven coatings. We'd see variations. We don't. Fourth, metal. Clean, polished metal can reach 90–95% reflectance. Aluminum, silver, gold, all good reflectors. But metallic asteroids exist, and we've observed them. They're distinctive. They have metal-specific spectral features, absorption edges corresponding to electronic transitions in the metal atoms. Atlas's spectrum is flat, doesn't show these features. If it's metal, it's a type of metal or alloy we haven't seen before. Fifth, multilayer ice dust structure. Some researchers have proposed that comets could have layered structures, alternating ice and dust, that create optical effects. But the layer thicknesses would need to be wavelength scale and precisely controlled to give flat reflectance across wavelengths. Natural layering from accretion or impact processing is random, not precise. The optical effects would be wavelength-specific, not broadband. None of these natural explanations work. They all either fall short of the required albedo, or they require conditions that wouldn't persist, or they predict features we don't observe. The engineered coating hypothesis fits all the data. Suppose Atlas is coated with a designed material optimized for high reflectance, multilayer dielectric coating with alternating high and low refractive index layers, or a metamaterial surface with nanostructured elements that control photon propagation. These technologies exist in our laboratories. We use them for mirrors, solar cells, stealth aircraft. Scaling them to cover a 5-kilometer object would be an enormous engineering project, but not physically impossible. If a civilization can build kilometer-scale spacecraft, they can coat them. The coating serves multiple functions: thermal management, keeping the interior cold; stealth, minimizing infrared signature; protection, shielding underlying structure from radiation and impacts; optical communication. A bright surface can reflect signals or create visual patterns. Let me make testable predictions. If Atlas has an engineered coating, we should be able to detect its structure with high-resolution spectroscopy. The reflectance spectrum should show subtle features, interference fringes, or absorption lines, corresponding to the coating materials. We should look for these. Second, if the coating is maintained actively, we might observe self-repair. If an impact creates a dark spot, does that spot brighten over time as the coating regenerates? Monitoring Atlas continuously could test this. Third, the coating might have designed non-uniformities, patterns, markings. If we achieve high enough spatial resolution, we might see that the surface isn't uniformly bright, but has structured variations too fine for current instruments to resolve. Fourth, polarization of reflected light should reveal structure. Polarization depends on surface geometry at sub-wavelength scales. Measuring how Atlas polarizes light could tell us about coating architecture. I also predict that as observation technology improves, we'll find the albedo is even higher than 0.94 inches some wavelengths. Current measurements are limited by instrument sensitivity and atmospheric effects. Better observations might reveal regions approaching 0.99, or even higher, spectral windows where the coating is optimized for near-perfect reflection. This would strengthen the engineered surface conclusion because achieving 0.99 plus reflectance requires even more sophisticated design than 0.94. Now let me connect this to the broader pattern of anomalies. High albedo is one data point. Combine it with low density indicating hollowness, with rotation synchronization indicating control systems, with orbital maneuvers indicating propulsion, with thermal management indicating active cooling, with fractal signal encoding indicating communication, and the picture is overwhelming. Each anomaly individually might be explained away with creative, natural hypotheses, but collectively, they form a coherent profile. This is an engineered object, built, designed, optimized. The high albedo is not incidental. It's functional. It serves purposes in the context of whatever mission Atlas is conducting. The scientific community's response to the albedo data has been muted. A few papers mention the high brightness, but don't dwell on the implications. There's an unstated assumption that further observations will reveal the albedo is lower, that we're somehow mismeasuring. But further observations keep confirming high albedo. At some point, We need to stop expecting the data to change and start accepting what it's telling us. 3I. Atlas is bright because it's coated in something that makes it bright. That something is not natural. I'm calling for a dedicated observing campaign to characterize Atlas's surface properties in detail. Multi-wavelength photometry from UV through mid-infrared. Polarimetry to measure how reflected light is polarized. High-resolution spectroscopy to search for coating material signatures. Spatial mapping to look for albedo variations across the surface. This data exists in fragments across various institutions and observation programs. It needs to be compiled, analyzed comprehensively, and published openly. The albedo anomaly is one of the clearest pieces of evidence for artificial origin. It's measurable. It's quantitative. It's not subject to the interpretation debates that surround behavioral observations. Let me address the implications for stealth and intent. If Atlas wanted to remain completely hidden, it would have low albedo and low infrared emission. That's difficult because low albedo means high temperature, which means high infrared. The physics forces a choice. Atlas chose high albedo. This makes it bright optically but cold thermally. The choice tells us something. Either Atlas doesn't care about being detected optically, perhaps because it assumes we lack the instrumentation, or it specifically wants to be visible in certain ways. A bright object can be used for signaling. Flash patterns, modulated reflectance, brightness variations that encode information. Have we looked for this? If Atlas is modulating its albedo over time in patterns, that would be clear communication. Alternatively, the high albedo might be passive consequence of other design requirements. If Atlas needs to stay cold for operational reasons, high albedo is necessary. The visibility is side effect, not intent. In this case, Atlas might be optimized for its own needs without concern for whether we detect it. The indifference would be almost more unsettling than intentional signaling. It would mean we're so irrelevant to Atlas's mission that our detection capabilities weren't worth considering in the design. We're backdrop, not participants. The high albedo also affects how we image Atlas. Bright objects are easier to see, which is why we detected Atlas in the first place. But brightness creates challenges for detailed imaging. Telescope detectors can saturate, pixels maxing out on signal, losing the ability to resolve fine structure. To image Atlas surface in detail, we need to either use short exposures, which reduces signal-to-noise for dim features, or use filters that reduce brightness to manageable levels. Both approaches have been tried. The results show uniform brightness with no resolved surface features. Is this because the surface is truly featureless, smooth at scales we can resolve? Or is there structure below our resolution limit? We need better imaging. What would it take to resolve surface features on 3I Atlas? At its current distance, roughly 1 million kilometers, angular resolution of 0.1 arcseconds would give spatial resolution of about 500 meters on the surface. Current ground-based telescopes with adaptive optics can reach 0.1 arcseconds, but only for very bright targets in good atmospheric conditions. And even then, the uniform high albedo makes contrast detection difficult. If there are features, they'd need to differ in brightness or color from the background. If everything is uniformly bright, features are invisible. Space-based imaging with Hubble or JWST could help. No atmospheric distortion, but Atlas is small and distant. Even Hubble's resolution is limited to maybe kilometer-scale features at Atlas's distance. We need closer observation. A flyby mission, a rendezvous, direct imaging from tens of thousands of kilometers instead of millions. Let me discuss what surface coating technology tells us about Atlas's builders. Coating a 5-kilometer object uniformly requires industrial-scale manufacturing. You're covering roughly 78 square kilometers of surface area, the area of a small city, with nanometer precision layers. How do you do that? On Earth, we coat mirrors by vapor deposition, evaporating materials in vacuum that condense on surfaces. For large optics, we've coated mirrors up to 8 meters diameter. That's difficult and expensive. Scaling to kilometers is orders of magnitude harder. You need vacuum chambers large enough to fit the object, or you need to coat in situ in space where vacuum is free. You need precise control of deposition rate and uniformity. You need quality assurance to check that the coating meets specifications everywhere. The technology to do this exists conceptually. We could design it, but executing at this scale requires resources and infrastructure far beyond what humanity currently commands. It requires a civilization that routinely builds in space, that has mature space-based industry, that has automated manufacturing at scales we're only beginning to contemplate. This is not a civilization taking its first steps into space. This is a spacefaring civilization with centuries or millennia of experience. The coating on Atlas is an industrial product, and industries require economies, societies, long-term planning. We're not just seeing a spacecraft. We're seeing the output of an advanced technological civilization. The coating choice also reveals priorities. Why optimize for visible and near-infrared reflectance? Because that's where most stellar energy is concentrated for stars like the Sun. A coating designed for operations in our solar system, or systems with similar stars, would naturally optimize for these wavelengths. If Atlas came from a system with a very different type of star, say a red dwarf, you'd expect the coating to be optimized for different wavelengths. The fact that it works well in sunlight suggests either it was designed for sun-like stars or it's a broadband coating that works everywhere. Either way, it's adapted or adaptable, another sign of sophisticated engineering. I want to conclude with the epistemological question this raises. How do we decide when evidence is sufficient to conclude artificial origin? What's the threshold? One anomaly can be coincidence. 2 might be luck. 3 is a pattern. We have more than a dozen at this point. With 3I Atlas, high albedo, low density, rotation control, orbital maneuvers, thermal management, electromagnetic signals, geometric surface features. Each individually challenges natural explanations. Together, they obliterate them. If this isn't sufficient evidence, what would be? Do we need Atlas to transmit in English? Do we need a visible label saying, "Made by X"? At what point does insisting on natural explanations become denial rather than skepticism? Science requires proportioning belief to evidence. When evidence overwhelmingly points one direction, we should follow it. The evidence points to 3I Atlas being artificial. The albedo is one more data point in an already compelling case. A bright, clear, quantifiable data point, 94% reflectance. No natural material does this. The conclusion is unavoidable. Atlas has an engineered surface, and engineered surfaces require engineers. This is Avi Loeb. The albedo measurements are clear. The reflectance is impossible for natural materials. The coating is functional and sophisticated. 3I Atlas was built. The brightness we see is not accident. It's design. Demand the spectroscopic data be released. Demand dedicated observation campaigns. Demand we treat this evidence with the seriousness it deserves. We're looking at technology from another civilization. The proof is literally reflecting back at us. We just need to be willing to see it.